Okay, by my clock, it's now 11:30, so let's get the next couple of talks underway. The first one will be given by Igor Oliveira.
Okay, thanks. This is joint work with Rahul. And my plan for this talk is to give you a sort of high-level overview of this notion of hardness magnification. And I'm going to be focusing on the main conceptual points. Okay. So a lot of research in recent years has gone into understanding connections between the design of non-trivial algorithms and proving superpolynomial lower bounds. And we have now a pretty decent understanding of these connections in settings such as satisfiability, de-randomization, learning. The topic of this talk is a bit dual to this approach for lower bounds. The game here is to extract from barely non-trivial lower bound proofs superpolynomial lower bounds. Okay, so in some sense, these two approaches are dual to each other. So here is the idea. We know that strong lower bounds are very hard to combine. And on the other hand, we have weak lower bounds in many computational models, such as formulas. So magnification theorem is a theorem showing the following. Starting from a very weak lower bound that is just barely superlinear, we will extract from this proof a superpolynomial lower bound from an explicit function. Okay? So during this talk, whenever I say superlinear, you should really think of n to the 1 plus epsilon, just to simplify the presentation. And this is an interesting approach because, as I'm going to explain shortly, it seems to avoid the natural proofs barrier. So remember that natural proofs sort of partitions the set of circuit classes into two worlds. On the one hand, we have the circuit classes that can compute pseudorandom functions. And for such classes, we have no lower bounds, or they're quite weak. And there are the weak classes where we have a variety of techniques, many of them combinatorial, and for which we can prove pretty strong lower bounds. And natural proof sort of says that whenever pseudorandom functions are in a class, we shouldn't hope to prove lower bounds using constructive techniques. So we would like to avoid natural proofs and to have new techniques to prove lower bounds against strong models of computations. So just to recall the definition of natural property, so that's an algorithm that is that runs in polynomial time in the input length. It accepts most of the input strings, but it rejects every string that has a short description, or it's computable by a small circuit. And by result of Ryan from a few years ago, and I think Ryan will be covering this result in his class during the semester. So roughly speaking, he proved that if you want to show lower bounds against an exp, then inevitably you're going to obtain a property that is at the same time constructive and useful. So if you want to avoid natural proofs, you should go for a violation of the largeness condition. Okay. Now, how does hardness magnification seem to avoid the largeness condition? The point is that, as I'm going to explain, the magnification approach applies to very specific problems. So from a barely superlinear lower bound for a function f, we're going to get a superpolynomial lower bound for a function h that is very dependent on f. And it's not clear at all how we would extract from just the superlinear lower bound for f superpolynomial lower bound for almost all functions. So the argument is very specific to some function that depends on f. Okay, so this is sort of like the heuristic argument for why magnification is good in the sense of natural properties. And now let me tell you a bit about what has been said in this direction of magnification, sometimes using different names, but the results are all, they have the same spirit. So to my understanding, the first theorem that is stated in this language of magnification is this one by Srinivasan from 2000. So he looks at the clique problem on undirected graphs. So the input length is n choose 2, m. And he considers the problem of approximating the size of the largest clique in the graph, but for a huge approximation factor. Okay, so it's almost linear in the number of input vertices. And he proved the following. If one can show a superlinear lower bound on the complexity of this problem for randomized algorithms, then you get that NP is not contained in BPP. So at least for this very specific problem, super linear lower bound implies a super polynomial lower bound for another explicit problem. But one of the goals of this hardness magnification line of work, at least to me, is to make these theorems as close as possible to settings where we can show lower bounds and perhaps get new unconditional lower bounds using magnification. So this is a problem that seems to be very hard to analyze. So you need to prove lower bounds against huge approximation factors for clique, and also in a model for which you don't really understand so well, right?
Is this uniform or non-uniform?
He has several different results in this paper. He has results for uniform and non-uniform settings. Now, much more well-known result in this area is this one by Eric and Michal from 2008. And they show a way to separate NC1 from TC0. And the theorem is the following. So there are some NC1 complete languages such that if you can show a super linear lower bound against TC0 circuits for this language, then you get that NC1 is not contained in TC0. Okay, and follow-up work of Lipton and Williams, they proved a similar statement with respect to size depth lower bounds and for a function in polynomial time. Okay, so these are very interesting results because they tell us something about hardness of proving superlinear lower bounds in some models. But if you want to use these theorems to actually get new lower bounds, you're in trouble because, for instance, if you look at the Allender-Kautsky theorem, you need to prove superlinear lower bounds for TC0 for some very specific functions. And we don't have these lower bounds even if you go all the way up to NE. Okay, and similarly, I'm not aware of any kind of size depth trade-offs for a function in P. So an interesting question here is, can we prove such magnification theorems in settings where we do have lower bounds? Okay. And very interestingly, a result along these lines was established last year in the setting of proof complexity. So here is a theorem by Moritz Müller and Ian P. Now, I'm talking about proof complexity only in this slide. So they show that there are some specific tautologies of size m. And if these tautologies require bounded depth Frege proofs of almost linear, like superlinear size, then we can get super polynomial size lower bound for Frege systems, which is like a major open problem in proof complexity. So the interesting aspects of this result are the following. First, lower bounds for bounded depth Frege are known by work of Aitai and many other people. And at the same time, the specific tautologies that they employ in this theorem, they were investigated before this work. They are just the truth table tautologies encoding the hardness of some Boolean functions. And work of Razborov, for instance, has proved that such tautologies, they don't have short proofs in res k of certain values of k. So we now have a magnification theorem in a setting where we can prove lower bounds. Not yet for the specific tautologies, but that seems to be progress with respect to the previous theorems I mentioned before. And what we ask now is, can we prove similar magnification theorems in the setting of circuit complexity? Because often circuit complexity is easier to understand than proof complexity. Yes?
So it would seem like, from what you're describing the tautologies, that if you actually prove the tautologies, you get a circuit lower bound. Or at least like this would give you a kind of uniform proof of the tautologies would give you
Why is that?
a useful property.
This is saying like a superlinear lower bound on the proof length implies a super polynomial lower bound.
Yeah, but if you
So-
had even like a polynomial proof,
Yes.
wouldn't you get of these tautologies? Wouldn't that be a useful property?
Depends on.
See which functions have such.
Also, the notion of uniformity plays a role in these connections between natural proofs and lower bounds. So maybe we'll take it offline. Okay, so now let me tell you about some new results in the setting of circuit complexity. And in some scenarios where we do have lower bounds. So these are new magnification theorems that they seem to be closer to the lower bounds we currently have in complex theory. So our results, they give a few examples of magnifications, of magnification theorems, and crucially, these results are in settings where we do have unconditional lower bounds. And in this work, we don't know yet how to prove lower bounds for the problems where we have magnification, but we will observe that there are closely related lower bounds for other problems. Okay, so in this talk, I'm going to be covering magnification for variants of MCSP, graph problem, and 3-SAT. Okay, in each case, I'm going to define a problem Q, and just a very weak lower bound for Q gives a strong lower bound for some explicit problem. And this is a sound approach to lower bounds, because if you make standard assumptions, these weak lower bounds, they should hold, and actually much stronger lower bounds should be true. And these weak lower bounds, they're really just barely non-trivial. Okay? So let's start with the simplest example, the k-vertex cover problem. So given this undirected graph using the adjacency matrix representation, so the input length is m, and we're going to understand if there is a vertex cover of size k. Okay, so our first theorem is magnification from AC0 lower bounds. So remember, AC0 is an extremely weak model. You cannot even compute the parity function. And we show the following. Let k be log n to the c, where c is a large constant that we can pick. If for every depth d there exists an epsilon such that k-vertex cover cannot be computed by almost linear size circuits of depth d, then NP requires super polynomial size formulas. Okay, so you can reduce the NP versus NC1 problem to the investigation of the complexity of this graph problem with respect to AC0 circuits of almost linear size. And for this choice of parameter, k log n to the c, if you assume ETH, then the complexity of the problem should be exponential in omega of k. And for this choice of k, this is going to be super polynomial. Yes?
What is m here?
M is the input length, n choose 2, the adjacency matrix representation for the problem. Okay, any questions about this statement?
So, where is C the conclusion?
No, you can pick C large enough, and then you show a lower bound for that fixed C against AC0 circles. Okay, so now let me move to the second example of magnification. You have already seen the minimum circuit size problem. Now, we're going to be using an average case variant of the problem. So this is about the definition of the problem. I'm going to be talking about worst case lower bounds later on. So here now we have two additional parameters, alpha and beta. And the yes inputs are the truth tables that can be alpha approximated by circuits of size at most s. So alpha is just the fraction of inputs where the circuit gets correctly. And now the no inputs are the functions that cannot be beta approximated by circuits of size s. In our result, alpha is actually going to be 1. So yes instances are just functions with small circuits. But we're going to be using a small gap for the no instances. So these will be the functions that cannot be, let's say, 0.99 approximated by circuits of size s.
Is this an average case variant or a gap variant?
This is going to be a promise problem because you have these functions between alpha and beta. But when I say average case, it's just the notion of complexity for strings when I define the problem. So this is worst case promise problem. Okay. Now our theorem here is the following. Let's pick the size parameter for MCSP to be 2 to the literal of n. And let's pick the average case hardness parameter to be 1 minus delta, where delta is exponentially small. Okay. So this is almost MCSP, except that the no instances, they cannot be, let's say, 0.99 approximated by a small circle. Now, if this problem cannot be computed by formulas of superlinear size, if the required formulas of superlinear size, then NP is not in NC1. Okay. So this is an example of magnification from very small formal lower bounds and how it implies NP is not in NC1. And the hardness certificate here for the problem is that even this version of MCSP clearly defines a natural property. So if you believe cryptography is secure, then this problem should be much, much harder than just for almost linear size formulas. Okay, so now let me tell you about some closely related lower bounds for this problem. So here's the set of instances. We have the easy functions that can be exactly computed by circles of size S. And here's a set of negative instances. There's a time gap, and they are average case hard with respect to this tiny gap. So if you want to establish NP is not in NC1, then the parameters for the problem are S is 2 to the epsilon n, where epsilon goes to 0, and the delta is exponentially small as well. So we need to show this doesn't have formulas of size n, capital N to the 1 plus epsilon. Capital N is the input length for this MCSP problem. And what is known is that if you look at the standard worst case version of MCSP, then the problem requires formulas of almost quadratic size. So now you can look at this lower bound proof and try to understand what are the hard instances employed in this lower bound proof, right? Because the set of yes instances is the same for our problem and for MCSP. But we have this tiny gap for the no instances. So the question is, are the no instances using this lower bound also a bit far from the yes instances or not? And in terms of the size parameter, this lower bound is pretty good for us compared to magnification. S is sub-exponential. But if you inspect the proof, the lower bound is going to use a delta parameter, which is actually tiny. It's much less than 2 to the minus 0.999n, where for magnification, we cannot handle a delta that is so tiny. So the message is that the hard instances produced by this lower bound, they're pretty close to the border of the easy functions. And that's the reason why we cannot combine magnification in this particular lower bound and prove that NP is not in NC1. But at least like informally, you seem to be close to it, but technically, that's not clear at all. Okay, any questions about this discussion?
With the size parameter, you have the epsilon is like 1 over square root n, right? I mean,
Yeah, for magnification, it's enough that epsilon goes to 0. So this is definitely enough for it. It's just the gap here that's not sufficient.
Can you say, like, so is it like additive error, or is it really like a worst case thing? You know what I mean? Like in the actual lower bound.
So the no instances, if you change a small number of positions in the truth table, they become easy instances.
So it's really
that's what I mean.
additive error. Like I'm just wondering, like you said, it's much smaller. Can you quantify that like a little bit more?
Yeah, so the delta there is less than 2 to the minus 0.99n. And the delta that we need here cannot be so small. Yeah. Okay, and the last result I want to mention is a connection between the 3-sat lower bounds and the randomization. So we know that this is one of the frontier questions in this area. Can we separate an X from BPP? And we would like to connect this de-randomization frontier to proving superlinear lower bounds for 3-sat. So this will be the ideal connection. So on the one hand, we have the problem of showing like weak lower bounds for 3-sat, showing that 3-sat is not in almost linear time algorithms, maybe with randomness. And on the other hand, we would like to understand if BPP is not large enough to compute the whole of NX. So the ideal theorem will be something like if 3-sat requires superlinear time, then NX is not contained in BPP. So somehow understanding of what happens in the near linear time regime can tell us something about polynomial time computations in general. But unfortunately, we don't know yet how to prove this version of the theorem. We can prove something along these lines if we use the notion of refuter. So a refuter is something a bit stronger than just showing that 3-sat is not in BP time. We would actually need to find an algorithm that produces hard instances for a candidate 3-sat algorithm. Okay, so this is the formal statement. Suppose that for every probabilistic machine that holds in nearly linear time. M here is the bit length representation of the 3-sat instance. So suppose for every algorithm running in this time and using just polylogarithmic many random bits. Now there exists a polynomial time deterministic machine. So this is this refuter R. And this machine on infinitely many input lengths M, it gets 1 to the M and outputs a 3CNF formula of length M. And for infinitely many values of M, these formulas, they witness that A is not correct with high probability over that instance. Okay, so you witness infinitely often formulas where the algorithm is not correct with high probability. And you are allowed to pick the refuter after you see the algorithm. So for every algorithm, you can design your refuter. So if that is possible, then an EXP is different from BPP. Okay, so this is a stronger requirement than just saying 3-sat is not in BP time n to the polylog M. We also need this refuter. And comparing to previous work in this area, if you had a deterministic SAT algorithm, then we know how to build a polynomial time deterministic refuter. This is allowed to run for more time than the SAT algorithm. And at the same time, if you had a randomized SAT algorithm, we can build a randomized refuter. So the reason this theorem doesn't imply an EXP is different from BPP is that we need a deterministic polynomial time refuter for randomized algorithms running almost linear time and with just polylogarithm many random bits. Any questions about this statement?
This use pseudo-random generator? No, it doesn't. The proof.
It uses the easy witness method and a bunch of other things. Okay, so one way you can interpret these results is that this partition between weak and strong circuit classes is somewhat illusory, or at the very least, it depends on the problem for which we're trying to show lower bounds. Okay, and at least in theory, it is sufficient that we focus on the weak models and get a much better understanding of these weak models if you want to show lower bounds against like polynomial size formulas. But at least in theory, you can reduce these problems to a better understanding of weak classes. Okay, now I still have a few minutes. I want to tell you about the general template for some of these proofs, not for all of them, but the idea is quite simple. So I have this problem Q, and we're going to show if it doesn't have, let's say, linear size circuits, then there's some explicit problem H that is connected to Q that requires super polynomial size circuits. So the natural approach here is to argue using the contrapositive. So we're going to assume that H is easy. So it has circuits of size n to the k for a fixed k. And we're going to use such circuits to design an almost linear size circuit for Q. Okay? And for this to make sense, because this guy here has circuits of size n to the k, which is not linear, you want to reduce the instances of Q to instance of H of subpolynomial size. And then you can apply slightly larger circuits. Okay? So the rule of the game is just somehow try to compress the inputs of Q into like smaller pieces and then to use some auxiliary circuit to solve the problem. So this is the general template, but the technical details, of course, are going to be very different in each theorem. Okay, but that's the general idea. So now I just want to tell you about the main ingredients in some of these proofs. So the first theorem I mentioned about the graph problem, k-vertex cover, and how you can investigate NP versus NC1 by just proving superlinear AC0 lower bounds. For this problem, what we're going to be using is some ideas from parameterized complexity, so how you compress an instance to a much smaller instance. And we're also going to be exploring the power of AC0 to actually make this entire computation very efficient. Okay. So that's important, understanding of the class for which you're showing the magnification theorem. And finally, we can use some simple connections between NC1 and AC0 circuits to make the connection between the two classes. Okay? It's not a hard proof. Now, for the average case version of MCSP, we employ some intuition, some ideas from learning theory. And the intuition here is that somehow if if you take a random projection of the truth table, you still get information about the answer to the original question. Okay, so this, like, you need to sort of define this new compressed version of the problem in an appropriate way. This can be done. And you also need to handle randomization here. You need to de-randomize the argument, but this is not so hard to do. And finally, the connection between 3-SAT and an X versus BPP, it's a bit more complicated than the other proofs, and we need to combine a few theorems here, such as highly efficient versions of the PCP theorem, easy witness method. So the compressed, the succinct version of 3-SAT is not so easy to define, need to be done in a very careful way. And to implement this argument, we need also to handle different notions of time-bounded Kolmogorov complexity. So this is a more complicated proof than the other two proofs. Okay, so let me tell you about what I think are the main problems in this research line. To me, one of the most interesting ones is, can we use hardness magnification to prove new lower bounds? And I think this is like a good approach to lower bounds because somehow it combines the power of the class, so upper bounds, with lower bounds. And our experience in recent years is that exploring upper bounds is also something interesting in connection to lower bounds. So this seems to be going in the right direction because of this. Second question is, are there barriers to magnification? Is there like a deeper reason for why we cannot prove these weak lower bounds that are necessary for like separations such as NP versus NC1? And finally, can we prove a generic hardness magnification theorem in Boolean complexity? So the results I mentioned here, they hold for like specific problems, but we have more general theorems in other contexts, like this work of Mark Russell and Shah and Ivan, where they prove generic magnification for non-commutative arithmetic circuits. I think it would be extremely interesting if something like this also holds like for Boolean circuits.
This is a tightening of earlier party of Amirio Dayoff and Pavel.
Oh yeah, yeah. Yeah, that's true.
It's the same result like yours, n to the 1 plus epsilon implies exponential, but they make it tight.
Yeah. Okay, now I want to tell you about some new results that we posted online this week. These theorems that I presented in this talk, they showed magnification around linear size lower bounds. And a natural question here is, can hardness magnification maybe shed some light into like existing frontiers in circuit lower bounds? For instance, lower bounds for formulas near the cubic barrier. So it's not clear to me that there is a precise explanation for this barriers or these frontiers in terms of magnification. But I want to tell you about a specific example that is somehow connected to this. Okay, so I mentioned the magnification theorem for average case MCSP and this closely related lower bounds. And because we know how to prove the lower bounds for the worst case version of MCSP, and understanding the worst case version of the problem seems to be easier, it makes sense to try to prove magnification theorems for the standard worst case version of the problem, right? And like Rahul said, we have a theorem along these lines for MCSP. But I want to mention another result which somehow extends to more general settings instead of just polynomial size circuits. It also works for like bounded depth circuits. So if you change the notion of complexity of strings from circuit size to some variants of time-bounded Kolmogorov complexity, we are able to use like standard techniques to sort of make the transition between worst case and average case hardness. And then we can prove magnification theorems for worst case versions of the problem, okay? And the intuition is that these worst case versions, they should be easier to analyze and to prove lower bounds. But as soon as you get these worst case versions and the magnification theorems, the magnification thresholds, they tend to appear slightly above the current lower bound frontiers in many, many models of computation. So for instance, for this problem Q, we can show magnification near the cubic frontier, implying an X is not in NC1. And at the same time, we can unconditionally prove that this problem is not computable by formulas of near quadratic size. So we can get magnification theorems in this new work for worst case versions of the problem, where we can analyze these problems and prove lower bounds for them. But the magnification threshold often goes above non-lower bounds. So this happens in many circuit models. It doesn't happen in all of them. And another theorem from this new work is, like Rahul explained, the first magnification result for the worst case version of MCSP. And here there's something very interesting compared to the previous theorem that I explained, which is that we really don't know how to compress MCSP, like the worst case version of the problem. Okay? It's not clear if you can reduce an instance of length capital N to an instance of length just S. So we need to use new ideas here to prove the magnification theorem. And the template is not exactly the one I presented before for like the general case. And finally, in this work, we use these magnification theorems to point out what could be a possibly new approach to separate X from NC1. And if you look at the lower bounds we already have in the paper, if you could extend these lower bounds for a model where you have just an extra layer of parity gates at the bottom, that will be sufficient to separate X from NC1. So just in some sense, you're just like a layer of parities away from X not in NC1. But it's not clear to me how hard it is to understand this layer of parities.
So a layer of parities for AC0 to prove what separation
For-
MCSP not in this class.
So it's actually a layer of parities for formulas. So you allow De Morgan formulas to compute parities at the leaves. And you need to prove a superlinear lower bound for this variant of MCSP that talks about time-bounded Kolmogorov complexity. So we already have formula lower bounds, which are superlinear, but we don't have superlinear lower bounds when you also have the parities. And if you can do that, you get that X is not in NC1.
But we have it for a different problem.
Say again?
We have it for a different problem.
Yeah, we have for the different problem. We need to show for this specific one. Yeah, so yes, this was just advertising the paper. Check ECCC for more details, and thanks.
Questions?
Yes?
You explained how to possibly get new unconditional bounds based on magnification. Do you know if you can redirect known unconditional lower bounds in like a simpler way?
No, I think it's a very good question. If you can just analyze the weak models and get different proofs of existing lower bounds. I haven't worked in that direction, but I think it's a very good one too.
Any other questions?
Yes, Ryan?
So you have magnification from worst case lower bounds in CSP. So is it for like NCSP or like a gap version approximately?
It's a MCSP in the usual sense. There's a tiny gap between the yes and no instances. So technically, yes, you need like the smaller instances to be of size, let's say 2 to the little O of n, and the other instance is like 2 to the little O of n times n. So there is like a tiny gap between the two, yes. Yes?
Have you tried to use this framework to prove new kernel kernelization bounds? Like that some kernelization would imply separate bounds?
Yeah, so in some sense, the kernelization theorems, if you can implement the reductions very efficiently, you can view them as magnification theorems, always. But we have examples now of magnification theorems that don't go in this direction. You actually need to do something else.
For example, SAT you can't kernelize on the polynomial hierarchy collapses. So that's a case where you can distribute.
Yes?
Yeah, to check. So, your results imply that superlinear AC0 bounds for vertex cover would imply NP is not an NC1. But I guess does this have to be? Would a general bound on vertex cover be sufficient, or does it have to be these specific instances?
So it has to be for this particular choice of k, which is log n to the c, where c is a large constant. So we are at a very special regime of parameters where we can do the magnification in almost linear size AC0, and we believe the problem to be hard. So you need to explore this very small regime of parameters.
Any more questions?
Thank you.